All right, so let's get started with our first topic video for lesson 1, and we're going to be looking at 3 important vocabulary terms related to how we understand and graph polynomial functions. Keep in mind that during class I mentioned we don't need to talk about polynomial graphs in really crazy detail because we do have graphing calculators that can do complex graphing by themselves. They don't need our help to do it. But it is important that we can internalize the meaning of polynomial functions enough to be able to identify, for instance, if we graph a function and it doesn't come out the way that it should. So we want to just have a basic working understanding of how polynomial graphs should behave. So thinking of that, take a look at these 3 vocabulary terms. I have them organized in a kind of an organizer just like we had in class. Vocabulary, symbolic meaning, and graphical meaning. So let's take a look at the first vocabulary term, which is degree, or you could write out degree of a function, because whenever we talk about degree related to polynomials, we talk about the degree of a function. And actually, let me write polynomials up here so we remember what we're talking about. So remember, polynomials are things like y equals 3x to the 7th power plus 10x to the 6th power plus x squared minus 5. That's just totally random. But a polynomial is a string of a bunch of power functions. So here we have a 7th power, a 6th power, a squared, and a -5, which is just our constant term. And we string them all together and we get a polynomial. Okay, let's now talk about what the degree of a function is. In words, the degree is the highest power of a polynomial. So in order to understand what the greatest or the highest power is, it's important that we write our polynomials in standard form, which is descending order. Kind of like my example up here, we have a 7th power, a 6th power, a squared. Now notice we could have had a 5th, 4th, 3rd power, but we didn't. But we've still listed them in order from highest, 7, down to lowest, squared. 7, 6, 2, and then we put the constant term last. So symbolically, the highest power is right here at the beginning. So it'd be y equals, I'm going to write it like I did in class today. That made everybody gasp. A sub n to the times x to the nth power plus everything under it, dot, 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 eventually plus c. The highest power is just, it should be right up here at the front, as long as it's written in standard form. So we look at this leading term, and we look at the power. So not anything that probably the words didn't suggest to you. The highest power of a polynomial. So you look for the term that has the greatest power, and that number is the degree. So in our example up here, our degree of the function is 7. We're going to talk about what that means graphically, but in order for me to totally give you meaning to what that's going to look like graphically, I need to also explain some of these other terms. So let's look at the next term. That's the leading coefficient. A coefficient is a number that's multiplying a variable. So in our example up here, 3 is a coefficient, 10 is a coefficient. Over here we actually technically have a 1 that's a coefficient, because it's multiplying x squared. And this is not a coefficient, it's just a regular number. We call that a constant term. So we have 3 coefficients here. The leading coefficient is the coefficient of the highest powered variable. So we just said that the degree here is 7 because x to the 7th, that's the highest power. The leading coefficient would be the one out front here that's multiplying. It'd be 3. So symbolically, in my crazy little expression that describes what a polynomial is, I know, don't get a headache. It's all these dot, dot, dots and letters and crazy things. It's just the number out front of the highest power. So in the case, again, of our example, 3 would be the leading coefficient. What's important here, I should write something out here. Let's see. We'll say the number multiplying the highest powered variable. And that's the leading coefficient. Again, graphically speaking, in order to make total meaning of this, I have to define all of my terms first. I do want to mention that the positive or the positivity or the negativity of the leading coefficient is very important. So I'm going to make a little note to self. I'll do it in a different color so we can see it here. Note to self. Plus or minus is really important. Sometimes, actually most of the time, the value of the number is going to be less important than whether or not the number is positive or negative. So right here, the leading coefficient is 3, but what I'm usually going to care about is the fact that it's a positive 3 and not a negative 3. So we'll keep that in mind. Leading coefficient, the number out front, but yes, the positivity or negativity does matter. Last vocabulary term for this video is the end behavior of a graph. And remember in class, I talked about how we can have 4 different types of end behavior to a graph. And we'll use the example of power functions to describe it. We could have a parabola, which has, let me actually get I'll draw the pictures and then I'm going to change the color. An upside down parabola, a regular cubic graph or an Egyptian, and a reversed or a negative Egyptian graph. And the end behavior refers to the tips of the function, where it starts and where it ends. And keep in mind that we talk about starting and ending from left to right. So for instance, this would be a start high, end high graph. Start high, end high. I like to use a little positive signs because they're a nice, easy, symbolic way of pointing that out. The second one here, that would be a start low, end low, because you start drawing down and then curve up and end back down. This graph would be a start low, end high. And this one would be a start high, end low. So we talked about that in class, but if you want to write it into your notes, you can write it in right here. That's what end behavior is. Now, what does that mean in a polynomial? Because remember we said, you don't have to write this down just yet, but we said that a polynomial graph can look pretty crazy. Like here's an example, here's another example, here's another crazy example. All kinds of crazy things can happen with polynomial graphs. And they don't all look the same. In fact, they can wiggle as many times as the degree of the function. So if the degree is 100, it could go up and down 100 times. I should say it can cross the x-axis 100 times. If the degree of the function was 10,000, it could go up and down and cross the axis 10,000 times. Or if it's just a degree of 3, it could cross 3 times. So there's a lot of variation to how many bends and twists will exist in a graph of a polynomial. But there's something that's much more predictable than those bends and twists and where they're going to be, and that is the end behavior of a polynomial function. And here's how we figure out what the end behavior is. So I'm going to kind of draw a cross. We use 2 pieces of information. We look at the degree, so we're going to be repeating ourselves here, and we look at the leading coefficient to see if it's positive or negative. So leading coefficient, positive or negative. And, whoops, giving us a little random dot. Go away. There we go. All right. So if we have a polynomial function, let's say it's y equals negative 3x to the 7th minus 3x squared plus x plus 1. That will be our random polynomial. So it is a polynomial because everything is a power function. X to the 7th, x squared. We have regular x, that's technically x to the 1, and then a regular constant term here at the end. And I want to decide what the end behavior of the graph is. And I'm telling us that the degree and the leading coefficient are the secret to our answer. So let's go back to our colors here. Let's do green, something new. First, let's decide what the degree is. We check to see if this is in standard form. Is everything in descending order? 7th power, squared power, 1 power, number. Yes, that works. So the leading the degree of the function is the highest power, which in this case is 7. So we'll leave that there, and we'll talk about what it means in a moment. The leading coefficient, we want to know if it's positive or negative. Again, we look at the term, the highest power, which is this one, and we look at the number in front of it, which in this case is negative 3. And just as I mentioned in our first example that I had written kind of up here at the top right, I care less about the 3 and more about that negative. So the leading coefficient in this case is negative. So we have a degree of 7 and a leading coefficient that is negative. And our question is, what does that tell us about the end behavior of our polynomial graph? And here's the wonderful, beautiful thing about it. Remember we talked about how all odd power functions behave, oops, didn't mean to cross over there, divide these. All odd power functions behave like one of these two examples on the right, and all even power functions behave like the functions on the left. If it's a positive even, it's, so like x squared, or x to the 4th, or x to the 6th, or x to the 10th, or x to the 100th, they're all going to look like this. If it's a negative even power, like negative x squared, or negative x to the 4th, or negative x to the 100th, then it behaves like this. Similarly, if it's a positive odd, like x cubed, or x to the 5th, or x to the 7th, or x to the 99th, it's going to behave like this Egyptian that starts low, ends high. And if it's negative, no matter what, cubed, 5th, 7th, 99th power, if it's a negative odd power function, it's going to behave like this, start high, end low. And the same is true for the polynomials. So look at this. We have information. We know that this graph is going to behave generally like a function with a degree of 7. So that means it's going to behave generally like an x to the 7th function, and more specifically like a negative x to the 7th function. So the degree is 7. The coefficient is negative, so generally speaking, it's going to behave like a negative odd power function. So what does that tell us about the end behavior? It tells us that it falls into this category right here, a negative odd power function. It doesn't tell us about all the wiggles in between. We don't know anything about the wiggles, but it does tell us that this function is going to start high. Up here, it's going to start high, just like our end behavior of the odd negative, and it's going to end low, just like an odd negative power function. It could wiggle. We don't know anything about the wiggles yet. Who knows? Maybe it looks like that. Maybe it looks something different. But what the end behavior tells us is where it starts and where it ends. And we call this starting high, ending low. And again, we found that information using the degree, x to the 7th, and the leading coefficient, it was negative. Keep in mind, polynomials can have a whole lot of information. This didn't matter to us, this didn't matter to us, that didn't matter to us. Only really the leading term mattered to us in talking about end behavior. All right, we're going to talk about that a little bit more in class. Make sure you have all those pieces of information down. I'm actually going to give you a video where I do one or two of these examples, and all we talk about is just finding the end behavior. We're not going to graph too much yet. We're just going to look at a function and decide if it starts high or low, and if it ends high or low. And that's it for this first topic video.